Hey, so on Discord, Nguyen Du Tan, I hope that's a good pronunciation of your name, presented a problem that had to do with the pseudometrics and equivalence classes. Yeah, I thought I'd just make a video to go over it. So first of all, we need to know what is a pseudometric. Pseudometric. So given a set x, then a pseudometric on x, it is a measure of distance, hence the metric, that goes from x cross x into the into the non-negative reals. So let's write it like that. And that is of course not enough. It has to satisfy three conditions, and those are very similar to metrics. In fact, every metric is a pseudometric, but it has to satisfy that for all x, small x, that is that's an element of big X, we have to have that the distance from x to itself is 0. We have to have that the distance is symmetric, right? So if we just switch the order, we should get the same number, right? The distance from x to y is the same as the distance from y to x. And finally we do have the triangle inequality, and that basically says that if you're going from the point x to the point c, that will always be shorter, or at least as short as taking a detour around y. So that means that the distance from x to c is let me just erase this. Hope you're okay with that. But this should be smaller than or less than taking the detour, right, from x to y plus from y to c. All right. You've probably seen a metric space before, and if you have, you'll notice there's one thing missing, right? What makes a pseudometric a metric? And it's kind of like an extension of the first condition that says that if the distance from x to y is equal to 0, when that is true if and only if x and y are actually the same point. And this is since this is a pseudometric we're dealing with, this is in general not true. So that means, what does that mean? That means that there may be x distinct from y, where we still have the distance from x to y is 0. So one way you can maybe think of it is if you have your set here, right, then we have all these points within x, but some of them maybe clump a little together, right? So each of these clumps are kind of indistinguishable, right? They're kind of the same point. If you're familiar with the topological spaces, this is kind of the metric version of not being housed off, right? If you don't know, the metric version of not being housed off, right? If you don't know about topological spaces, just forget about that. All right, so now we're ready to actually look at the problem. Let me just find it. It is here. Okay. So this is the exercise we're going to do. Right. So we have D is a pseudometric on some set X. And in the first exercise, we define a relation. So we say that X and Y, understood to be elements of big X, we say that X and Y are equivalent if and only if the distance between them is 0. So if you imagine it had actually been a metric, that would mean that all of these sets would be singletons, right? Because there's only one point that has distance 0 from you, and that's, well, it's you, is the point itself. But since this is pseudometric, these equivalence classes might actually be bigger than 1. But first of all, we need to show that it's an equivalence relation. Okay. So what does that entail? Well, first of all, it needs to be reflexive. What does that mean? Well, it means that we must have that X is equivalent to itself. But since we already, this is a pseudometric, so we already know that the distance from X to X is 0. And that is exactly the definition of X being related to X, right? So that's the reflexive condition. Then we must have symmetry. So that means if X is related to Y, then Y is related to X. So let's assume that X is related to Y. What does that mean? That means that the distance from X to Y is equal to 0, right? But since the distance function is symmetric, that also means that the distance from Y to X is 0, and hence that means that Y is related to X. Okay. And finally we need transitivity. Right, so here we assume that X is related to Y and Y is related to C, and then we want to show that X is also related to C. You can kind of skip the middleman, right? Alright, so these two things mean that X, the distance from X to Y is 0, and the distance from Y to C is 0. And we want to show that the distance from X to C is also 0. So let's, because in that case they're equivalent, let's try to calculate the distance from X to C. And yeah, sorry, we don't want equality here because we want to use the triangle inequality. So if we take a detour to Y, so basically we are writing exactly the identity down, right? The distance from X to Y is always smaller than or equal to the distance from X to Y plus the distance from Y to C, right? It's the detour. But we know that each of these are 0, right? This is 0, this is 0, so it's 0 all in all. And since the distance between any 2 points needs to be 0 or larger, well, we can conclude that the distance from X to C is actually 0, so that means that Y is equivalent to C. Alright. So that was the first question. Now we have an equivalence relation. So what we kind of done is we've clumped like the clumps I showed you here. So the equivalence classes in this case would be this point is isolated, this point is isolated, but all these points, this cluster of points, they will all be lumped into the same equivalence class. This is isolated, and this one also clumps together, right? So in this toy version of cartoons, there'll be 6 equivalence classes. Okay. So I hope that is intuitive. But in the second problem, we consider the canonical map P, which is from X into the group, the set of equivalence classes, right? We write it like this with this fancy division notation, and in particular the element X is sent into the equivalence class containing X, right? And this map in particular, in general, it will not be, well, it will be surjective, but in general it will not be injective, because we can have equivalence classes with like the clumps, right, with a lot of points in them, several points in them. All right. But we need to show that there exists a unique metric. A unique metric called D prime, and it's a unique metric not on X but on the set of equivalence classes, and it satisfies that the distance, the new distance between one equivalence class, so we can write a general equivalence class like this. So this is another way of saying the equivalence class containing X and the equivalence class containing Y. So there is a unique metric that will satisfy this. Right. So the D without the prime is a pseudometric, and the D with the prime should be an actual metric. Okay, so first of all, we can see here it looks like this equation will uniquely define this metric, if it is indeed a metric, but it seems to at least uniquely identify the mapping. But the thing is, we do not know if this is well defined, right? Because here we've chosen X and Y as representatives for two equivalence classes. But what would happen if we had chosen other representatives? Who knows? Then we might have gotten another right side. The distance between those representatives might be different. Okay, so we want to show that this is in fact well defined. If it's well defined, it will also be unique, right? Because this uniquely tells you what the mapping is. Okay, so is the prime well defined? And in order to show this, we let's choose an arbitrary. Choose an arbitrary x0 that is an element of the equivalence class containing X, and Y is a unique, no, not unique, it's an arbitrary element in the set. An arbitrary element in the equivalence class containing Y. So we want to show that no matter what the choice of these, then we should still get the distance from X to Y. Right? So how can we show this? Well, so if X0 is in the equivalence class containing X, that means that X0 is equivalent to X. Similarly, Y0 will be equivalent to Y. What does that mean? Well, it means that the distance between X0 and X is 0, and the distance between Y0 and Y are 0. Okay, so let's try to calculate or see if we can say something about this distance from x0 to y0. So what we can do here is we can use the triangle inequality. So let's first take a detour over the point x, right? So we can do this. We kind of insert x into the path, right? But what we see here is that the distance between x0 and x, that is simply 0. This is 0. So what is this? This is simply the distance from x to y0. But then we can play this game once again, and this time we will kind of insert y, take a detour to y. So this is less than or equal to, sorry, greater than or equal to x to y plus y to y0. And again, this is also 0. So this is simply the distance from x to y. Oh, that's almost impossible to see. All right. So what we've kind of achieved is, okay, we kind of achieved one inequality. If we can kind of establish the opposite inequality, then we will have that these two quantities, these two distances are in fact equal. So let's see, we do the exact same thing, the exact same strategy. This time we start with x and y instead of x naught and y naught. So this will be less than or equal to the distance from x to x0, kind of plus the distance from x0 to y. And once again, we have this nice property that the distance from x to x0, because of the symmetric property, that is also 0. All right. Then we can take a detour over y0. So that would be d from x0 to y0 plus d from y0 to y. And once again, this thing is also 0. So what we get is that we just have the distance from x0 to y0. So what have we done? We have shown that the distance between the 0 points, the arbitrary points, and x and y, well, we have one inequality there, and we have the opposite inequality here. So the only possibility is that d from x to y is in fact equal to d from x0 to xy. So yay, we are very happy. Because, well, this is what we wanted to show. This shows that the definition of the metric, or at least the mapping, we have yet to show symmetric, that this is well defined. So that's awesome. Is the prime a metric? Okay. So first of all, it needs to satisfy all the things that a pseudometric must satisfy. So let's start with those, right? So first, what is the distance between an equivalence class and itself? Well, we can see per definition, this is the d prime. So by definition, this is the same as the distance from x to x, or rather the pseudo distance. And d is a pseudometric, so we know this is 0. So that's good. That's the second one. We should have that the distance between one equivalence class to another equivalence class, it should be symmetric, right? We can swap these. So let's see, what is this? Per definition, this is the distance from x to y, but because the distance, pseudo distance, is symmetric, that is the distance from y to x. And then again, using the definition, we have that this will exactly be what we want it to be. Oops. All right. So These are both good. And almost similarly, we need to show the triangle inequality. So we want to compare the distance from the equivalence class containing X to the equivalence class containing C. But what is this? By definition, this is the pseudo distance from X to C, but this is still pseudometric, so the triangle inequality holds. Right? So we can kind of insert the Y taking the detour. Oh, that got really ugly. Right? But then again, we can use the definition of d prime to see that this is exactly what we want it to be. All right, so that one is also good. So the thing we really need is the thing that makes a pseudometric a metric, right? So that means if the distance from X to Y is 0, that forces X to be equal to Y. Oops. So assume that the distance from the equivalence class containing X to the equivalence class containing Y is 0. So what does that mean? Well, that means that the pseudo distance from X to Y is equal to 0. But that is exactly the same as X being equivalent to Y. And this is exactly the same as the equivalence classes being the same, right? X and Y must belong to the same equivalence class. So that means we're done. Yeah, that turned out to be long, but I hope it helped.